And
Okay.
you can get started.
Hello and welcome to Gardening a Changing Climate. My name is Steve Savage. I will be your host and your tour guide on what I believe is a fantastic journey through 540 million years of Earth's history as we explore the Phanerozoic Aeon and its changing climate. And the reason for that is to see if we can gain any insights into our own changing climate and how we might live and garden within it. I truly hope you will find it as interesting and informative as I have, at least as I researched the material, wrote the material, and present it to you today. But first, let's do a little bit of housekeeping to set the stage. The course consists of 5 parts, each about an hour and a quarter long, and spread over 1 week or over 1 week apart over 5 weeks. This first one's probably going to be a little bit longer than that, maybe an hour and a half, just simply because we've got some housekeeping to do on top of the normal presentation. I would like to point out to you that there are, you'll see numbers in parentheses on the slides and in the text if you choose to view it on the Master Gardener website. These refer to the references used. Those references are listed on the last 2 slides in part 5 and on the last 2 pages of the text. And there are about 30 of them, I think, in all. In addition, you will see asterisks on some of the slides and in the text. These also refer to references. These references are listed on the text page or the slide, either at the bottom or in the middle of the page or slide. They're given in this manner because they were late additions, and rather than add another page of or another slide of references, we just simply put them where they were as they were introduced. The slides and text are available on the website, which is shown on the closing slide at the end of part 5. Should you download either slides or text, be aware that there are 143 pages of text and 67 slides. Now again, before we get started, I'd like to show you a couple of the references that I think are important, and these are book type references. Most of the references are articles out of scientific magazines and stuff, but these are actual books that I used. And the first one is called Oxygen, a 4 Billion Year History. It's written by Donald Canfield. It is really when we first wrote this course, we were going to go all the way back 4.5 billion years ago and bring you up to the present date. That got a little bit long. We probably need another 3 or 4 parts to do that. So we cut it, and we cut the first 4 billion years of history out and just began about 560 million years ago. This book talks about how the atmosphere was oxygenated, and a lot of that occurred in that first 4 billion years. It's a little bit technical for you chemists. There are a lot of chemical equations in it, but they're mostly in the appendices, so if you don't want to read them, you don't have to. He does use some technical language, but I would say that the average reader, if you just kind of skim over that, you can still get the gist of what he's saying. It's very interesting. I would certainly recommend it. The next references is the one called The Ends of the World, and it's written by Peter Brannan. This it deals primarily with the 5 mass extinctions. It's a very, very easy read. There's not, I don't think there's any real technical information in it, so you can read it and enjoy it. I would tell you that in the case of Oxygen, Donald Canfield's book, that's reference number 1. And I think you're only going to see that referenced 1 time in the current presentation. The Ends of the World, on the other hand, you'll see it's reference number 7, and you're going to see it referenced a lot of times, particularly when we get to the session on mass extinctions. And the reason for that is that's what he dealt with. And what I've done when I actually directly quote him, and if you look in the text, there'll be quotation marks around that, and then the number 7 in parentheses after it. But since I drew so much information from his book for the 5 mass extinctions, you'll see up on the slides and in the text up on the title where it says like the Devonian mass extinction or the Ordovician mass extinction, you'll see the dates and then you'll see the parentheses 7. That just means that since a lot of the material in there is from him, but it's also mixed in with other material, it's mixed in my comments, so I didn't know how to properly credit him. So it's just up there in that top, it says I drew a lot of the information from him, and he really should get credit for that, and that's how. The last two extinctions, somehow it got left off, but it ought to be on them also. The final references are reference is the Volcanoes of the Cascades by Richard Hill, and it's not listed in the references because I don't specifically reference it, but we talk a lot about volcanoes, particularly the volcanoes in the Cascades, and this is just it's an easy read. It's kind of a pamphlet book. You could probably read it in one sitting if you wanted to, and so if you're interested in volcanoes, particularly the Cascadian volcanoes, this is I think a really nice, really good reference to look at. So with that then, let's go ahead and get started. This is our Master Gardener slide, and if this course was originally written to be done in person, and we didn't make it in time before the coronavirus struck, so here we are on Zoom. But I would tell you more about the Master Gardeners. You can read this. If you're really interested in Master Gardeners, becoming a Master Gardener, just call the Cooperative Extension Office, tell them you are, and they will give you the information that you need. So then, I would like to point out to you that the Earth is not a toy. You know, we all have toys, whether we're adults or whether we're kids. We play with them, we use them, we break them, we get tired of them and cast aside, and we go down and buy the next toy that we're interested in. Well, obviously, the Earth is not a toy. We break this toy, or we break this Earth, and we can't go down to Macy's or Home Depot or something and buy a new Earth. It doesn't work that way. So with that in mind, I would say that we need to treat Earth as if it were our home. That little blue dot you see floating in the inky blackness of space above the lunar horizon there is all there is, folks. Every person who ever lived, every animal that ever, or plant that ever existed, every thought that was ever thought, it all occurred on that little blue dot right there. If you get closer to the disk of the Earth, instead of 240,000 miles away, say only 400 or 500 miles away, and take a picture, you'll see a bright line all the way around the Earth. It's usually about 1/8 to 1/4 of an inch wide. That is our atmosphere. That provides us with the oxygen we breathe, the water we drink, the rainfall that waters our gardens and all the other plants on Earth. And it also provides us with protection from most of the UV radiations coming from the sun. So it behooves us to take care of that atmosphere and not use it as a garbage can. So then treat the Earth as if it were your home, because in reality, it is. So a brief look then of what we're going to do. Obviously introduction, this is some introductory material. We'll get some more in just a minute. Then we're going to look at climate controlling processes, how the Earth regulates its climate and therefore the temperature and how we live. The next section is mass extinctions. And we'll look at the 5 major mass extinctions, again, seeing if we can draw any parallels, any conclusions to what is happening today. And in fact, we're going to compare mass extinctions to today, again, to see if we can draw any conclusions from them. We'll look at human influences, how we are affecting the climate, and what impact that has on Earth. Then we'll look at the consequences of proceeding as usual. In other words, if we keep doing what we've been doing, what likely will be the consequences of that. And then finally, the last section, what can be done, which reflects basically where this course is going, all this other materials leading up to this last section, what can be done. And we get a little bit on what governments can do, but most of it focuses on what we as individuals and as gardeners can do to either mitigate or maybe even prevent some of the changes that are occurring and are going to occur. So that's kind of the course. So today, we're going to be discussing the Earth's changing climate and how it will affect each of us as we live and as we garden. And we'll look at how our children, and much more consequentially, our grandchildren, will also be affected. I realize I'm not stupid. I realize this subject has been politicized and polarized to the extreme. But I would like to put the politics aside and look at this from purely a scientific perspective. Recognize that this isn't a political issue, even though it's been made such. It's a scientific issue. Indeed, the University of California requires that I teach only science-based information, and that's what you're going to get in this course, science-based information. The truth is, thermometers are not political beings, okay? They simply record the temperature. And what they are recording is an ever increasing global average temperature. The same can be said for carbon dioxide measuring equipment. They are recording ever increasing atmospheric carbon dioxide levels. And we will learn why increasing carbon dioxide is particularly distressing and concerning in just a couple of minutes. To try to put this then in some perspective, we are going to look at the last 5 mass extinctions events that have occurred over the last roughly 560 million years, and how some of the occurrences then might be instructive again of what is happening today. Why they only last 560 million years? Well, there wasn't much to become extinct before then. In fact, the Phanerozoic aeon, which began about 542 million years ago and goes to today, is the aeon that has been ongoing, is the aeon that we live in. And Phanerozoic actually means visible life, as life before then was too small to be visible. It was just single cell creatures, or to leave much of a record in the fossil record. So we don't really know if there was any extinctions then of these single cell creatures, probably not. It's only been in the last 560 million years that multicellular life has existed and developed and has left a record for us to examine. So let's take a look then at the essential elements that are critical to life on Earth. And the ones you see there on the screen then are those elements. It's their interactions that make possible life as we know it. So let's look at their effects. The first one then is energy. There are 2 primary sources of energy for creating and sustaining life: the sun and chemical reactions between elements, chiefly between hydrogen and oxygen, or with hydrogen or oxygen and iron, sulfur, or carbon. The energy provided by these sources provides the energy that drives and sustains life. So let's digress for just a moment and return to the early Earth. For the first billion years, there really wasn't any life on Earth. Then, by some unknown process, single cell creatures known as methanogens collectively developed around hydrothermal vents on the ocean floor. They used the chemical spewing from the vents as a chemical energy source to produce the energy for their lives. Life still exists around hydrothermal vents even today, and they are still living on chemical energy. There's also life in subglacial lakes in Antarctica that also lives through chemical energy. That's about all there was for the next 1.5 billion years. But the problem with methanogens was they could not move very far away from their vents. So life was constrained to the immediate vicinity of the vents, leaving the rest of the oceans lifeless. Probably sometime toward the end of that 1.5 billion years, something truly earth-shaking happened. By yet another totally unknown process, some of the organisms developed or acquired a substance called chlorophyll, and they are called cyanobacteria, and it is the beginning then of photosynthesis. That allowed them to use the sun's energy to drive their life processes, freed them from the hydrothermal vents, and life could then spread throughout the ocean. Cyanobacteria then filled the oceans for the next 1.5 billion years up to the Phanerozoic Aeon. During the period leading up to the Phanerozoic, 2 other earth-changing events would occur, and we'll discuss them in a future session. So let's look at water then. Water both dissolves the elements of life and it transports them through the earth, aiding in erosion and sediment disposition and deposition, as well as carrying them through our own bodies in our blood. The 5 elements you see then form the basis of life on Earth. So water, then looking at critical temperature now, water probably originated from outgassing from the early Earth's interior and from delivery by comets and asteroid impacts. Now, I just read a week or 2 weeks before the recording of this event in early September of 2020, that all the water needed to fill the oceans existed on Earth from its formation, and that only a small fraction arrived by comet or asteroid. Now that's a huge change from what we've been thinking here for the past, I don't know how many years, how many decades, that we didn't need comets and asteroids to bring water to us, that it was already here and it outgassed and formed almost all the water. Yes, asteroids and comets probably brought some, but most of it was already here. We're going to have to watch for more studies to see how this problem is resolved and what the final analysis is. The existence of liquid water on Earth's surface then is a result of the Earth being in something called the habitable zone of its star, and the existence of carbon dioxide in its atmosphere, which we'll discuss in a minute. So liquid water, of course, is essential, again, for life as we know it on Earth. Presently, Earth sits just within this habitable zone, 4.5 million miles closer to the sun, and we would be too hot for liquid water to exist on the surface. Earth will eventually, in about 500 million to 1 billion years from now, be inside the inner limit of the habitable zone as the sun intensifies, as all stars do. And when that happens, then the habitable zone will move outside the Earth's orbit, and we will be inside the inside edge of the habitable zone, if you can figure that out. And when that happens, then the oceans will boil away and the Earth will become uninhabitable. Having trouble with that word today. In fact, the sun's intensity was only about 70% of what it is today. 4.5 billion years ago, by the beginning of the Phanerozoic Aeon, that intensity had increased to about 94% of today's value. So you can see it is increasing. And of course, today it is 100%, but it'll be more than 100% as that habitable zone continues to creep and out and as the sun further swells and intensifies. So the Earth's atmosphere then is a mixture of gases, but 3 are of prime importance. Nitrogen, which is about 78% of the atmosphere and basically is an inerting agent. Oxygen, about 21% of the atmosphere, which is obviously what we breathe. And then everything else forms about 2 or 3% of the atmosphere, and the chief gas there is carbon dioxide. Carbon dioxide is the primary greenhouse gas in the atmosphere, along with water vapor and methane. Presently, there is enough carbon dioxide in the atmosphere to absorb heat and maintain a livable temperature. And why is that important? we need to talk just briefly about something called the Earth's albedo. Well, what the heck is an albedo? It's just simply the reflectance by the Earth of some of the sun's energy that strikes Earth. Currently, the Earth's albedo is about 30%, meaning that 30% of the sun's energy falling on Earth is reflected away, which then means that Earth loses this amount of radiation that could be used to warm the planet. Without carbon dioxide and its greenhouse effect then to offset that heat loss from the albedo, Earth's temperature would be about, on average, 5 degrees Fahrenheit, which is obviously too cold for liquid water to exist. If, on the other hand, carbon dioxide levels were much higher, then the Earth would be too hot. So let's move on then to some of the look at some of the natural processes that control Earth's climate, including the crucial role that carbon dioxide plays. So as you can see here, right there at the top in bold letters, the Earth's climate is primarily controlled by the amount of carbon dioxide in the atmosphere, and that in turn controls the atmospheric temperature. The processes also control how materials are sequestered and recycled on Earth, and why that is important for ancient history, for today, and for the future. I would like to point out to you the bottom one, Earth's orbit, is also a contributing factor of climate change, but it doesn't have anything to do with carbon dioxide particularly. But it is a climate change controller. So then let's look at the very first one then, plate tectonics. So as the Earth's surface cooled, it was molten to begin with, it cooled and formed a crust. And as it further cooled, the crust thickened. And that caused it to contract. And as it contracted, then it began to crack into huge plates. It's like, for you oceanographers, I guess, it's like what happens when seawater freezes. Although when seawater freezes, it doesn't contract, it actually expands, which is a good thing because it makes it more buoyant. Otherwise, all the ice would sink to the bottom of the ocean. It's only barely buoyant. If you're familiar with icebergs, 4/5 of them are below the water. Only about 1/5 is above the water. But it's buoyant enough that it floats on the surface. That expanding sea ice cracks. And then wave and wind action pushes some of those plates together, uplifting them to form pressure ridges, kind of like mini mountain ranges. In other areas, the plates pull apart. And that forms open water leads. Well, the crustal plates are not driven by wind and wave action, but they are driven by movements in the molten magma below. There are actually circulation systems in that molten rock below. And where they push the plates together, as you see up there, the denser plate dives below the less dense plate, and that's called subduction. The less dense plate is pushed up, forming mountains, just like in ice pressure ridges. When the plates are pulled apart, great rift valleys or deep depressions form in the crust. Again, think of open water leads. The crust becomes thinner and the mantle closer to the surface. So as you can see then, plate tectonics is the primary producer of volcanism. And volcanism produces carbon dioxide, which is put up into the atmosphere. With subduction, the crust of the descending plate pushes deep into the mantle where it melts. Carbonate in the crustal plates melts, and we'll talk about carbonate in just a minute, and reconstitutes some of that carbon dioxide. But the carbon dioxide stays in solution with the molten rock because of the tremendous pressure it's under. The lighter plate is thrust upward to form a mountain range. Cracks and faults in that upthrust plate allow magma from below to ascend upward. It's looking for places of least resistance, and there's less resistance in those cracks and faults. As it does so, the pressure is released, and that allows some of the carbon dioxide to come out of solution. As the magma rises even higher, the pressure falls more, allowing still more carbon dioxide to come out of solution. Groundwater is also vaporized, adding to the pressure. until the whole mass gets high enough up that the rock pressure is no longer sufficient to hold it, and then it erupts from the surface to form lines of volcanoes. And those volcanoes are usually stratovolcanoes, although they can also be something called a shield volcano. Stratovolcanoes, those big conical mountains that we see and we think of as volcanoes, whereas a shield volcano, the magma just comes up and flows out and builds layer upon layer upon layer. Actually, Hawaiian Islands are shield volcanoes. So, but think here, if you will, then the Cascades, where we have a line of stratovolcanoes extending from Mount Lassen in the south all the way up to Mount Baker, which is up in British Columbia. There are also shield volcanoes in the Cascades, and two of them, for example, the Newberry volcano in eastern Oregon, which is between the Three Sisters complex and Crater Lake. Remember, Crater Lake was once a massive volcano, which I think was called Mount Mazuma, I believe is what it was, until it blew up. Also, there's the Medicine Lake volcano in northeast California, just northeast of Mount Shasta, actually. And the Medicine Lake volcano is actually the largest cascade volcano by total volume of lava put out. In fact, it is 10 times the size of Mount Shasta. In the Sierra Nevada, there's another shield volcano called Mammoth Mountain. You ever go down there and ski? There's a large pool of magma underlies this area, and it periodically the magma starts shifting around, causing earthquakes, which then raises concern about an eruption. Well, someday it probably will. Carbon dioxide dissolved in the magma under pressure is released into the atmosphere as the pressure is released. Think here again of a champagne or a Coke bottle, okay? The wine is put into the bottle, it's then pressurized with carbon dioxide, and pressure is added into the bottle to keep the carbon dioxide in the solution, and a cork is put in that to hold all that pressure in there. When you pull the cork out, that pressure, the pressure is then released, some of the carbon dioxide comes out of solution, and it blows the cork between your eyes if you're not careful, and it shoots a spurt of champagne, or possibly Coke, if you're talking Coke, up into the room. That is very similar then to what happens with a shield volcano or with a stratovolcano. With rifts, and you think of the Great Rift Valley in Africa, as the crust pulls apart, it thins, allowing the magma to break through and release basaltic flows. Again, with the pressure off, carbon dioxide is released into the atmosphere. Think here more of a glass where you're either going to pour soda or you're going to pour champagne into it. And if you do it too quickly, a lot of that carbon dioxide again comes out of solution, froths up the top, and if you're not quick enough to stop, it overflows the top and flows down onto the table or the floor or whatever. Well, that's very similar then to what happens with rift volcanoes. So an interesting note is that the Great Rift Valley of Africa is spreading apart. And I just read another article. It says in something like 1 million years, I believe it is, that will spread far enough apart that the two halves of Africa, west and east, will separate, the ocean will flow in, and we'll have a new ocean, which as that Rift Valley continues to expand, the ocean will get wider. Kind of interesting. It'd be interesting to be around to see it. So once again, volcanoes then are the natural source of carbon dioxide to the atmosphere. So let's look at something then called the rock cycle. And the Earth regulates its own temperature to some degree through this process called the rock cycle. And that then, so what it does is it regulates the amount of carbon dioxide in the atmosphere. And the amount of carbon dioxide in the atmosphere then regulates the temperature. More carbon dioxide, warmer. Less carbon dioxide, colder. Carbon dioxide is removed from the atmosphere by chemical weathering. And if you look at the chart up at the top, it shows plate tectonics, volcanoes, thermal vents and whatnot release carbon dioxide into the atmosphere. And then we get down to, on the right-hand side, the third there, we talk about weathering. So again, carbon dioxide is removed from the atmosphere by this chemical process of weathering. And what it is that as rainwater falls through the atmosphere, it mixes with some of the carbon dioxide and it forms a weak acid solution. Think acid rain, same deal. And that acid rain then falls down onto the rocks. It really likes basaltic rock, and particularly fresh basaltic rock, but in a pinch, any rock will do. And it reacts with the rock then, and that combines some of that carbon dioxide then with the rock to form carbonate, which we mentioned previously. The carbonate may stay where it is, or it may be eroded and washed down to the ocean. It carries a lot of nutrients with it, and as you'll see later on, that can enhance life in the oceans. And it can also produce massive algae blooms, which we'll talk about later on. But wherever it goes, eventually the plate that it's resting on is subducted, and then that subduction gets us back to where we were before, over on the left-hand side there, with the uplifting of the mountains, and returns us to volcanic activity, which puts the carbon dioxide back into the atmosphere. So carbon dioxide removal through weathering is faster with elevated temperatures, when the temperature is higher, as there's warm air can hold more water, okay? And therefore, there can be more rain, which produces more weathering. Weathering is slower with colder temperatures, as cold air can hold less water, so there is less rain and therefore less weathering. And so with less weathering, then the existing volcanoes can get ahead of the process and put carbon dioxide back into the atmosphere. So as the atmospheric temperature increases, carbon dioxide removal increases. More rain equals more weathering equals more carbon dioxide removal. With decreasing carbon dioxide levels, temperatures begin to fall, eventually leading to a cooler Earth. The opposite occurs with a cooler atmosphere. There's less rain, so carbon dioxide removal through weathering decreases. Carbon dioxide levels begin to rise, again because of those volcanoes that are out there, which add more carbon dioxide to the atmosphere, and eventually then the atmosphere warms. It's a neat process. The only problem is it's a really slow process. It takes millions of years to cycle this thing through. And so it can't respond quickly to rapid changes, and that gets us into trouble, as we're going to see. With the development of life, atmospheric carbon dioxide is also captured by that life, first in sea life, and then much later in life on land. As the sea life dies and sinks to the bottom of the ocean, as the sea life is developed, it takes carbon dioxide from the atmosphere, the marine plant organisms to develop. But as it dies, then it sinks to the bottom of the ocean. Some of it is decomposed, and we'll talk about that in a little bit, but it carries much of that carbon dioxide down onto the sea floor, where it forms carbonate limestone. The limestone is eventually subducted, volcanoes form, and then again, the carbon dioxide is released back to the atmosphere. Some sea life on the ocean floor also decomposes in a process, an anaerobic process. And anaerobic just means without the presence of oxygen. Aerobic is in the presence of oxygen, anaerobic in the absence of oxygen. So it forms then some very interesting compounds when it decomposes anaerobically. We call those natural gas and petroleum. On land, trees, well, any life, any plant life or any life, trees, especially those in coastal swamps or in bogs, die. They're covered over, and again, when they're covered over, they decompose anaerobically to form still another interesting element that we use today, and that one's called coal. Both of these processes then can remove carbon dioxide from the atmosphere, at least on a temporary basis. So I call that rock cycle kind of the long-term carbon cycle. Whereas the next one is, I call the short-term carbon dioxide cycle, and that's photosynthesis, although it can be long-term. If we would leave the coal and the petroleum and natural gas in the ground, it can be long-term. We're not doing that, but it could be. So during the day then, plants combine, the left-hand picture there, water, carbon dioxide, and sunlight in the presence of a catalyst called chlorophyll. And that produces the sugars and the starches that the plants use for their life cycle. And they release oxygen into the atmosphere as a byproduct. If I can digress just a bit, a lot of people think that the plants today are providing us with all the oxygen we need and so on and so forth. Well, they are putting some oxygen into the atmosphere, though not as much as you might think, and we'll see that in a second. But let me read you a quote, and this is from a man named Scott Deming from Colorado State University. And to quote him, "The oxygen we breathe is the legacy of photosynthesis in the ocean that over billions of years steadily accumulated oxygen, which made the atmosphere breathable. The oxygen could only accumulate because the plankton that produced it died and mostly sank to the ocean floor before they could decompose. Otherwise, their decomposition would have consumed the oxygen they produced. The processes that determine how much oxygen is found in the atmosphere, on average, occur over vast geological timescales and aren't really influenced by the photosynthesis occurring today," end of quote. So in effect, we are breathing prehistoric air, a relic of millions of years ago. So let's move to the middle picture there. Both day and night plants respire just as we do. They combine oxygen which they draw from the atmosphere, and the sugars and starches that they produce through photosynthesis to produce energy for the plant and plant materials for its structure. In that process, they consume oxygen and release carbon dioxide in the atmosphere, just like we do when we breathe. To the far right then, when the plant dies, decomposition recombines carbon in the plant with some of that oxygen that the plants produce that's in the atmosphere, okay, and releases carbon dioxide back into the atmosphere again. But not all the carbon recombines with oxygen. Some of the carbon is stored in the soil, where it can be used for new plant growth, and some is buried deeply in sediments where it may become rock or organic fossils such as coal. So soil storage then also represents a net removal of carbon dioxide from the atmosphere. But you can see all of that then, the oxygen that is produced by photosynthesis is nearly all consumed either in the plant's respiration or in decomposition. Only a tiny fraction of it remains in the atmosphere to kind of replenish what we are using. In fact, the biggest producer of oxygen for the atmosphere, the net gain, is phytoplankton off the Amazon River, where there are massive plankton blooms for some reasons, which you come to another course I teach, we'll talk about, but we don't have time to talk about it now. So that's where most of it gets added in, but still it's a tiny, tiny fraction. If you view atmospheric carbon dioxide from sensors in space, really a very interesting thing is shown, and that is an annual carbon dioxide oscillation in the form, mathematicians, of a sinusoidal wave or a sine wave. And that just means that it's like a smooth wave that goes up and it goes down, it goes up and it goes down. Okay. So what's causing that is that as you get into the fall and the early winter, all the deciduous plants now are dropping their leaves. The perennials are dropping their leaves and going dormant. The annuals are all dying. So photosynthesis, it almost ceases. The only thing left are evergreens, and even their photosynthetic processes slow down considerably. So we are no longer drawing carbon dioxide from the atmosphere for photosynthesis. The result of that is the wave begins to rise. As we get into the very late winter, early spring, all of a sudden the deciduous plants all leaf out again, perennials leaf out again, and new annuals grow. And now we begin to remove carbon dioxide from the atmosphere for photosynthesis, and so that wave begins to fall. We get to the fall again and the winter, and it goes back up, and it's just a never-ending wave cycle. I think you can see. I think there's a NASA website someplace where you can actually go and see that. It's really very interesting. The point then is, on the Earth today, not only the rock cycle and volcanism, but also life itself maintains the atmospheric carbon dioxide balances. So the question I would ask you then is, what does that imply as we destroy forests worldwide? And I'll give you just a second to think about that. And if you answered rising carbon dioxide levels, you get a gold star. So human-caused increases in atmospheric carbon dioxide concentration caused principally by the burning of all that stored carbon in oil, gas, and coal will inevitably increase the global temperature. The increasing temperature should cause an increase in rainfall, leading to increased weathering, and therefore an increase in carbon dioxide removal through the weathering and the rock cycle. And this should then cause temperatures to fall and take care of the problem, right? So what's the problem? Well, the problem is we are introducing carbon dioxide into the atmosphere at an accelerated rate. In fact, at an annual rate that is somewhere between 50 and 100 times more than all the volcanoes on Earth combined released annually. The rate of increase over time is faster than the events that led to the Permian extinction, which was the worst mass extinction to ever occur on Earth. The combination of human carbon dioxide releases and volcanic releases is simply overwhelming the system, putting more carbon dioxide into the atmosphere than can be removed by natural processes, that is, weathering, plants, ocean absorption, so on and so forth. The result then is an ever-warming atmosphere. Looked at another way, over the past few million years, atmospheric carbon dioxide levels varied between 200 parts per million up to about 280 parts per million. They were closer to 200 parts per million during ice ages and 280 parts per million during warm interglacial periods, such as the one we live in today. Pre-industrial revolution, the carbon dioxide concentration was somewhere between 270 and 280 parts per million. As of May 2019, let me just put in here, carbon dioxide levels in the atmosphere, one of the chief places they're measured is the top of Mauna Loa in Hawaii. And they're measured on it continuously, but they release the results in mid-May of every year. Why mid-May? I haven't a clue. I don't know, but that's when they do it. Okay. So as of May 2019, the carbon dioxide level in the atmosphere was slightly over 415 parts per million. And it had been rising over the past few decades at an average rate of about 2.5 parts per million per year. Although between 2018 and 2019, it actually rose by 3.75 parts per million. Okay, and it has been gradually accelerating throughout these last few decades, and culminating in this 3.75 parts per million between 2018 and 2019. In May of 2020, the average concentration had risen to just shy of 417 parts per million, which is an increase of only about 1.59 parts per million. Hooray! We've accomplished it. We are reducing the amount of carbon dioxide we put in the atmosphere. Happy days, huh? No, not really. Because a funny thing happened, or not really a very funny thing happened, starting about the end of January, early February of 2020. And that was a little something called the COVID-19 pandemic. And what that did, all you people who commute, no commuting anymore, the freeways are virtually empty. Airplanes stopped flying, ships stopped sailing. factories shut down, stop pouring carbon dioxide into the atmosphere. Transportation is one of the chief causes of the releasers of carbon dioxide in the atmosphere, and it was virtually shut down. And that happened for about the last quarter of the year, say mid-February through mid-May. So obviously, with the less emissions of carbon dioxide, then the rate of increase is going to decrease, and that's why you see that decrease to about 1.59 parts per million. Now, will that continue from 2020 through May of 2021? I don't know. I suspect it might. We are starting to put things back and more transportation and more factories, but it might still hold steady where we don't really go up as much as we have in the past, maybe higher than 1.59 parts per million, but maybe not as high as the past. But you know, the pandemic will one day end, we'll get a vaccine or something will happen, and the pandemic will go away. And then most likely we will return to our old ways and the carbon dioxide level increases will increase. The last time carbon dioxide levels hit 400 parts per million in the atmosphere was 23 million years ago. And at that time, sea levels were about 50 feet higher than they are today. And that has some major impacts also, and we'll discuss them much later in one of the future parts. So during periods of relatively stable carbon dioxide levels, which have been the case for the past few million years, at least until we came along, fluctuations in the Earth's orbit tend to dominate the climate, producing glacial and interglacial periods within the overall climate. Variations in eccentricity, axial tilt, and precession, collectively known as the Milankovitch cycles, and the guy Milankovitch, I believe was his name, who found this correlation. They make up the three dominant cycles. Changes in these three cycles create alterations in the solar radiation reaching the Earth's surface, and that directly affects the Earth's climate and impacts the advance and retreat of Earth's glaciers and therefore its ice ages. So let's look at each of these three cycles, and we'll start with eccentricity. Eccentricity is just the shape of the Earth's orbit around the sun, and it fluctuates on a cycle of about 100,000 years, and the fluctuation caused primarily by the gravitational attraction of the other planets in the solar system. And that alters then the distance of the Earth from the sun. The orbit varies from nearly circular, which is the fried egg you see there on the right. We were a little bit circle challenged when we drew that, to a more elliptical shape, which you see on the left, with the difference of the farthest point from the Earth to the sun between the circular orbit and elliptical orbit, increasing by about 12 million miles at maximum eccentricity. In today's nearly circular orbit, there is a variation of the energy received from the sun between the closest point of the Earth to the sun and the farthest point of about 6%. At the maximum eccentricity, remember we're 12 million miles farther away at the farthest point now, the variation then between the solar radiation received at the closest point and the farthest point is somewhere between 20 and 30%. Obviously, that has an impact on Earth's climate and its glacial regimes. At present, the orbital eccentricity is nearly at the minimum of its cycle. We are about as circular as we're ever going to get, and we're just starting to move towards maximum eccentricity, which we should arrive at in about 50,000 years or so. So my question to you again then would be, what would be the consequences for our climate with increasing eccentricity? And I'll give you just a second to think on that one. Okay, if you said colder or cooling, you get another gold star. You're really collecting those gold stars. So let's look at the next of the Milankovitch cycles, and this is called axial tilt. And the axial tilt then is the inclination of the Earth's axis in relation to its plane of orbit around the sun. And that plane of orbit, which is also known as the plane of the ecliptic for you astronomers, and you'll hear that term, it's a little easier than say the plane of the orbit of the Earth around the sun, just say the plane of the ecliptic. Okay, but it's thought that when the Earth formed, that its axis was pretty nearly vertical to the plane of the ecliptic. Okay, so this axial tilt then varies, as you can see, on a cycle of about 41,000 years. The tilt is believed to have been caused by Earth's collision with another protoplanet, which it says about the size of Mars, and that occurred about 4.3 billion years ago. That collision then vaporized the mantle, both on the proto-Earth and on this other protoplanet, sending it flying up into space. Well, some of it, as it cooled, some of it eventually fell back down, creating what would now be a new Earth, a combination of the old Earth and the protoplanet. But some of it remained in orbit around the Earth, where it eventually cooled and it coalesced, and it formed then the Moon. 4.3 billion years ago, the Earth was spinning on its axis much faster than today, with day length only about 6 hours long in today's hours. The combination then of the gravitational attraction of the sun, which existed, and now the moon, which has just been created, creates Earth's tides. The tidal action results in a drag on the Earth's rotation, gradually slowing it. And you can imagine then, with the moon being much closer, tidal fluctuations in first the molten surface, and then as the oceans formed in the oceans, the tidal range must have been fantastic, okay, as compared to today. So by about 400 million years ago, then day length had increased to where it was about 21 hours. And of course, today it is 24 hours. The rotation rate is still slowing, and perhaps you hear every few years on the internet, on the news broadcast or something else, that the Earth's timekeepers have added a leap second to their atomic clocks. Well, that is due to correct for the slowing rotation. The moon today is moving away from the Earth then at a rate of about 1.5 inches per year. And at some point, it's going to break the southerly bound of Earth and go flying off into space, either in orbit around the sun or out into interstellar space. So it's this tilt then that is largely responsible for our seasons. And it oscillates then between about 21.5 degrees to 24.5 degrees on a cycle, as you can see, of about 41,000 years. And the degree of the tilt affects the severity of the seasonal changes. Less tilt, that is moving more towards the vertical, more evenly distributes solar radiation over the Earth. This causes somewhat warmer winters, resulting in heavier rain or snowfall if you're in the area where it snows, because again, warmer air can hold more moisture. The heavier snowfall then perhaps doesn't all melt each year, and so it begins to accumulate, and that accumulation then forms ice sheets and glaciers. So we have heavier glaciers formation, even though the overall temperature on the Earth is a little bit warmer. Blows your mind, huh? I had trouble with it too, don't worry. More tilt accentuates the difference in solar radiation received at the poles, creating larger temperature differences between equatorial regions and polar regions. This tends to result in a somewhat cooler Earth with less rain, less snowfall, and then somewhat less glaciation. Currently, the axial tilt is about 23.5 degrees, or near the middle of its range, and it is decreasing, that it is moving towards more vertical. This should mean then a warmer atmosphere with more rain, more snowfall, which should enhance the rock cycle, removing carbon dioxide from the atmosphere, as well as increasing the growth of glaciers. Instead, we are seeing increasing carbon dioxide and decreasing glaciation. So let's look at the final cycle, then it's called precession. This is nothing more than the Earth's slow wobble on its axis as it spins. It's been likened to, a child's top, where when the spin decreases, it begins to wobble. That's precession. The slowing of the Earth's rotation on its axis is not causing precession in the Earth's axis. Instead, it's the gravitational attraction again then of the sun and of the moon, and it occurs on about a 23,000 year cycle, as you can see. The wobble periodically causes the North Pole to alternate pointing between either towards Polaris or towards Vega, resulting in significant climate variation. When the North Pole is pointing towards Polaris, as it is today, Polaris is the North Star, the Northern Hemisphere winter occurs when the Earth is closest to the sun in its orbit, and Northern Hemisphere summer occurs when our Earth is farthest away. This allows for a somewhat warmer Northern Hemisphere winter and cooler summers. When the North Pole points towards Vega, the opposite occurs. The Northern Hemisphere winter occurs when the Earth is farthest from the sun, and obviously the summer when it is closest. So the winters are somewhat colder and the summers somewhat warmer. Under the current orientation of the Earth's land masses now, the effect is not as dramatic in the southern hemisphere, as most of the land mass is in the northern hemisphere, not much in the south. It's mostly ocean, and oceans moderate the effect of any kind of temperature change. So at present, then we said the North Pole is pointed towards Polaris. It's our North Star. And so the Earth is closest to the sun in northern hemisphere winter. In about 10 to 11,000 years, that will reverse, and the Earth's North Pole will be pointed towards Vega. And that is just now beginning to happen. So we should be moving then towards colder winters and warmer summers in the northern hemisphere. The interaction of these cycles then can have dramatic effects on Earth's climate. Sometimes they overlap each other and reinforce each other, which then causes massive cooling or perhaps massive heating, massive glaciation, or massive warm spells. And other times they're out of sync and they don't line up, and then that will mitigate the effects and lessen the effects that any one of them would have caused. So it is these three cycles, but particularly precession or wobble, that human-caused climate change deniers use to say that it's all naturally occurring and not caused by humans. Well, they're right. It is. It's all naturally occurring. These three cycles naturally occur. We don't have anything to do with them. However, there's a fly in the ointment of their statement. In fact, there's two flies in the ointment. Fly number one is the degree of warming that is occurring today is much faster, at a greater rate than any of these three cycles could produce, even if they were all lined up, because those cycles occur over thousands of years, and the warming that is occurring today is occurring over less than hundreds of years. Fly number two, we are at a point in all three of the cycles where we should be moving towards increasing glaciation and another ice age, not towards global warming. So let's move on then and look at supercontinents, or continental formation, if you will. So over Earth's history then, numerous supercontinents have formed and then broken apart. It's all the consequences, again, of the land masses riding on the tectonic plates and the tectonic plates shuffling around on the Earth's surface. Note that the early supercontinents were not very large. In fact, they wouldn't even classify as supercontinents today. Most of them were about the size of a single continent today. Some of them were actually a little bit smaller. Some of their names and their orders of formation and breakup are Valbara, Ur, Kenorland, Columbia, Rodinia, and then what I would call the one true supercontinent, and the one most people have heard about, Pangaea. Now, between Rodinia and Pangaea, a number of other continents formed, and one of those is called Gondwana, and it was in the southern hemisphere, just right at the equator and slightly south. I would say Gondwana probably would classify as a supercontinent. Then there was one called Laurentia, which is in the northern hemisphere and the eastern hemisphere north of the equator. It kind of broke up, and then another one formed called the Old Redstone Continent, and that was in the northern hemisphere and the western hemisphere, kind of straddling the equator. And then it broke up, and still another continent formed, and that was called Laurasia, which straddled both the equator and straddling the northern or the eastern and western hemisphere. Laurasia then collided with Pangaea, or with Gondwana, and then that formed the supercontinent of Pangaea. Realize that the shape and location of the continents then was nothing like they appear today. So when I talk about Siberia or Europe or North America or Ukraine or anything like that, they looked much different and were not where they are today. For example, the old Redstone Continent makes up most of the eastern half of North America today. It's identified by the rock formations that existed then and still exist today. So you can find that same rock formation in the eastern half of North America today. So that's how that works. So the formation and breakup of supercontinents has much the same effect on volcanism as does the movement and collision or pulling apart of tectonic plates. Again, because it's basically the same thing. Continents are riding on the plates. Where continents collide to form supercontinents, there is subduction, uplifting, and volcanoes, as we show in the slide. The massive volcanic activity pours carbon dioxide into the atmosphere. This obviously affects the climate, and if it gets too much out of hand and can't be controlled by the rock cycle, it leads to mass extinctions. When supercontinents break apart, there is massive rifting. The plates pull apart, allowing magma to upwell, creating basaltic flows, and again, volcanoes in the basaltic flows, or perhaps shield volcanoes. This too, that all that magma up there is releasing carbon dioxide into the atmosphere, which again can dramatically alter the climate and perhaps lead to extinctions. So for our final topic today, we're just going to look at the how a supercontinent all by itself might modify the climate. So the existence of supercontinents then can have a dramatic effect on the climate of that supercontinent. But we don't need a supercontinent to get much of this to produce many of the same effects. A large continent such as Asia, Australia, or North America will do just very nicely for producing some of the same effects. The interior of a continent becomes blazingly hot if it's true if it's located close to the equator, and it becomes very, very dry, a desert, because moisture can't reach it. And in winter, it may cool down a little bit, but it doesn't cool down a whole lot. So it still stays relatively mild. And in the summer, of course, it's blazingly hot. So if you think of a continent like that today, look at Australia. On the other hand, a continent located closer to the pole, and let's look at Asia and particularly Siberia, but all that northern Asian part, much closer to the pole, the winters there get blazingly hot, or blazingly cold. I mean, blazingly, that's not the right word. They get terribly cold and freezingly cold, whereas the summers do warm up and get mild, but they don't get blazingly hot, okay? And then that can produce, again, Siberia would be probably the example of that. In North America, we can look at the interior parts of North America up through the plain states, particularly Montana, the Dakotas, and on up into Canada. And again, in the winter, terribly cold. In the summer, it gets pretty darn hot. Actually, the Dakotas, easily reach into the hundreds. In fact, 100 degrees even reach temperatures even occur up in Canada as well. So variations in this hot and cold produce strong seasonal onshore and offshore flows if there's an ocean nearby, and those flows are called monsoons. This can produce wet conditions along the coastline when onshore flows occur, and cool, dry conditions when the flow is offshore. So if we look at Australia today, you do get a monsoon flow during the summer months because you have very hot air in there drawing that moisture on. You don't get much of an offshore monsoon there because the temperature doesn't cool down as much. Go up to Siberia and up into Asia, and that's an entirely different story. There, during the summer, it gets warm enough to begin drawing air in, and you get what's called the southwest monsoon, which dramatically impacts Asia, or India rather, and Southeast Asia. So it's very hot, it's very humid. There are thunderstorms and torrential rains nearly every day, if not every day. The reverse occurs in the winter when it gets cold there, and that cold air sinks and flows out. And now you get something that's called the northeast monsoon. Again, the effect on Southeast Asia and India is now you have a cool, dry flow of air out. The humidity decreases. You still get rain showers, but it's not an everyday event. When I was in Vietnam, we look forward to the northeast monsoon because it was cooler, it was drier, not so rainy. And in the evening, sometimes if you were out, it actually felt a little bit chilly. Or if you happened to, we had open air showers. I mean, they weren't totally open air, but the air could flow in. And if you were taking a shower during the northeast monsoon, particularly in the early morning or in the evening, it was nice to stay under the warm water because otherwise it was a bit chilly. We also have monsoon. Oh, and those northeast monsoons then also flow down off the coast of China, where they produce bitterly cold outbreaks all the way across the Sea of Japan, and bitterly cold outbreaks in Japan as well. We have monsoon flows here in the U.S. too. Again, that hot interior of North America, the plain states, and the Dakotas, and on up into Canada, that draws moist, warm air off the Gulf of Mexico and funnels it up, and you get then thunderstorms and the like occurring up through the Dakotas and on up into Canada. You get upslope flow on the windward side of the Rockies and what's called the Front Range, and you get lots of thunderstorms that develop there as well. Some of that air also flows around the southern edge of the Rockies, where it combines with monsoonal flow off the Gulf of California, streams up into the Sierra Nevada, and we get thunderstorms there from that monsoonal flow, and some of those spill over into Nevada as well. In the winter, it gets cold, and now the flow is offshore. The final thing then is we look at coastal mountain ranges and how they have an effect. Again, if they're along the coast, let's just look at the Sierra Nevada because it's in our home, and Cascades. I mean, they're in our hometown virtually, so they very well show this effect. So the air over the ocean is relatively warm. It's very, very moist, obviously, lots of water out there, and it flows on land. As it flows on land, it hits this coastal mountain range, the Cascades or the Sierras. It is uplifted, and that's called orographic lift. So it's uplifted. As it rises, it cools. As it cools, it can hold less moisture. So some of that moisture has to come out, which it does. First as clouds, and then later on, it'll either be rain or snow. Once that air hits the top, much of the moisture has been rain or snowed out. And as it descends the other side, it actually warms, which increases its ability to hold water. It doesn't have much water left. There's no water over there, so now it's very, very dry. You get on the opposite side then, you get the deserts in Nevada, the Great Basin, even the eastern sides then of Oregon and Washington are very, very dry. Also, you get, remember that flow coming up the Front Range of the Rockies. It rains out there too, and as it comes over the top, it also is now deficient of moisture. It heats, and so you get this massive desert in the Great Basin. With supercontinents, then, these effects are magnified by 10 times or more, many times over anyway. So with that, then, we finish up today. I hope you have learned something. I hope you enjoyed it. And I hope you're eager to hear the next session where we're going to talk about the geologic timescale. Very briefly, we'll talk about the definition of a mass extinction. We're going to look at how carbon dioxide affects mass extinctions. And then we're going to look at the first three of the mass extinctions, the Ordovician, the Devonian, and the granddaddy of them all, the Permian. So I hope you will return for part 2. In the meantime, thank you for the privilege of your time, and we hope to see you next week.